I can't necessarily end early, but if we say are just about done, we might end early, or if we have a problem that would take more than 10 or 15 minutes to get through, we might. We definitely want to close that. There we go, so we don't get any weird feedback. But if anything did happen where you had to leave class like 10, 15 minutes early, something like that, the recording is still going to happen. And you can always come back to the YouTube playlist right up here under recorded lectures, and you can always catch that last few minutes. Well, other questions at the moment, folks, before we get started today? You bet, Quentin. Thanks for asking about that. And while we're talking about it, here is the recording so far. Like I mentioned, we're going to try to record every single class meeting, but mistakes can happen. So if a video is missing, it might have gotten to a different playlist, maybe the trigonometry class. Just email me and I'll try to get it fixed right away. And after a few years of doing this weird stuff, I have had like 2 classes where something just went wrong. The whole video was damaged. There's no way to get it back. That might not happen for our class, but if it does, it'll be extremely rare. So we'll just hope the technology keeps on working. Well, where we're at so far is in section 1.3, covering vector spaces. We have these 2 assignments on the table due next week. And pretty much the routine that we're going to get into, like we've mentioned, is once we complete a section, we'll give it a 1-week turnaround for the due date on the upcoming homework assignment. So we finished section 1.1 and 1.2 last class meeting. So there's 2 due dates on those. And section 1.3, if we complete this class meeting, it'll be due a week away, Thursday, January 25th. If we need to take an extra time on that, these due dates here are in flux until the actual section's completed. So if we need to take extra time on 1.3, say we finished it on Tuesday, this due date would just be revised to reflect the new 1-week turnaround on the date. Well, welcome back, though, folks. Well, let me get my other windows going. Here we are. So for today's class, we're doing some pretty interesting topics. We're looking at vector equations. It's kind of an innocuous looking concept there. But what section 1.3 is really trying to introduce, if we scroll further down into the Zoom, is section 4.1 on vector spaces. This is an early draft. It's the notes I used last year, and I revise my notes each year to try to look for better ways to present the problems, that kind of stuff. But if you wanted to take a look at my notes early, they're presented here. And it might not be a bad idea to just peruse that section, 4.1, a little bit early, maybe once we're running through chapter 3 and we're getting close to it. It helps out a tremendous amount just absorbing that information. I also put some optional reading down here, reading about Peano's axioms. These are the axioms of how the ordinary non-negative integers work. Euclid's axioms are the axioms of how plane geometry should work. And you open up section 4.1, these are the axioms of a vector space. So this is pretty much what a lot of modern mathematics looks like. We develop a system, give it axioms like these, and just see what can happen with the axioms. Back in the land of Euclid's axioms, here's what they looked like. Euclid had these axioms right here, 1 through 5. And based just on those axioms, this is considered modern geometry. This is the real deal of mathematics. Even though this is work that's thousands of years old, it's kind of amazing. We're really kind of doing the same thing with vector spaces. We just have a different set of axioms that we'd be working on. Likewise, there's other strange axioms if you're interested in these right here. But before we get too wild in that direction, we want to look at vector spaces like the ones we'll see here. These are going to be the vector spaces called R2, R3, Rn, and so on. And where it starts, well, I kind of scroll to a weird spot here. Where it starts is just introducing vectors in the first place. A vector space is just a set, and the collection of that set are objects which we'll call vectors. So if we are back to the typical kind of problems we're working on, like section 1.1, 1.2, we're dealt with matrices. They're typically augmented matrices coming from systems of equations. But we can also just introduce a vector or column vector. If we have 2 entries for our vector, there's what they would look like. 3, -1 for just a random vector, 0.2, 0.3 for another one. Or if you want to write down your vector arbitrarily, you would say the vector W gets Well, entry W1, entry W2. And in this course, we're going to assume that the entries are real numbers, although they could be complex numbers in other courses. So if we collect the set of all vectors with n entries, we'll put them into a set called Rn. But for our examples up above, all three of these vectors specified are in R2 because they're vectors with two components, two entries, or you could say two rows. Any questions with the notation so far? These R2 things or the vectors? Okay, well, R2 is going to be a pretty common symbol. So is Rn, R3, and so on. We're now describing vector spaces when we list these things out. And just as a reminder, if you've seen this notation before, R without any superscript on it is just saying the ordinary real number line in interval notation, negative to positive infinity. So these will be really common symbols we'll see in notations. Homework problems, the reading, and in the notes, they'll be kind of everywhere, starting with that one. And what gets a little bit confusing now, we have vectors, different symbols like these, is the zero vector. It's massively important to our work in linear algebra, and we denote it by that, 0. Usually it's going to be bold to indicate this is not a scalar, where we're talking about an ordinary real number. This is a vector that contains multiple entries. So just for a couple examples, if I were to write down the 0 vector on paper or say digital ink like this, I can't really write it bold. So the way I'll indicate that I'm dealing with a vector, so I'll just put a little vector symbol above it. So now this is not the number 0, it has entries. But we can write here that 0 vector in R2 is that same symbol, 0 vector, would be 0, 0 like that, only because we specified it should have came from R2. If we want a different example, we can say this thing, 0 vector in R3 is this vector. Because it's coming from R3, I'll have 3 different components, all of which must be zeros. So that's what the 0 vectors look like. And we have to compare them against 0 is a scalar in R. I feel like that deserves an exclamation mark because suddenly at this point in the notes and in our work in mathematics, that symbol right there is highly, highly overloaded. It depends on the context. It could mean a scalar. If it's bold, it's probably a vector. And if it goes along with the vector equations, it's probably a vector as well. Well, any questions, folks, about the 0 vector at the moment? Okay, well, now we've got vectors flying around. We have augmented matrices from section 1.1, 1.2, and they do link up. That's part of our goal in section 1.3. Compare the work we did prior with the new work, the new formatting, including vectors. And next most important thing we'd want to know, now that we're working on vectors, when are they equal? I put down a definition here for R2, but this is the same definition in R3, R5, or Rn generically. We'll say that vectors are equal if and only if corresponding entries are equal. Seems like a sensible definition, but really the most important word here is this, where it says corresponding. Without that word, if I look at these vectors, practically the same thing, right? 157, 175, what's the difference? Well, there is a difference. In entry 1 to entry 1, we have equality. The vectors could be equal, but from entry 2 to entry 2, it's a mismatch. So already on this problem, we would say, no, U is not equal to the vector B. Only because in the second position, or entry number 2, those two corresponding entries happen to be unequal. Well, any questions, folks, with our introductory topic so far? Okay, maybe not the most exciting example, but just a really quick illustration of vector equality now that we're putting down all these properties. Next thing we need is some kind of algebra with working on these vectors. There's some things we can do, some things we can't do. There'll be plenty of things that are undefined. For example, we won't use the cross product in this course, but that's an operation on vectors, an honest one in R3. Move this over just a touch. Here are the major operations that we're going to be using. I highlighted these and put them in bold just to try to highlight their importance. And when it comes to a vector space, say you're dealing with Rn or something more abstract, all you need is a set. That's a set of vectors with n components. On that set, define vector addition, scalar multiplication, and you have an honest vector space. It just so happens this example is in R3. Vector addition is going to be defined in the typical way we would expect. Take two vectors with three components. If you're going to do vector addition, we've indicated as u plus v. That's not your ordinary plus, it's a brand new operation, but it does a sensible thing. That plus there is the ordinary one. We're just adding corresponding components. If we're scaling a vector, we're dealing with scalar multiplication. C here being a scalar just says C times the vector u, scale every one of the components here, C times u1, C times u2, and so on. So we're just multiplying all entries. So that gives us vector addition, scalar multiplication. And I put this in brackets since we're not saying it just yet. We'll say it in 4.1, but just as a preview, that's all it took to make Rn into a vector space. We now have all these algebraic properties, but there are things that you might have taken for granted either way. For example, this is the commutative law of addition. It says you could take a vector u plus v, get a result, which would be the same as v plus u. In other words, v can commute to in front and u into the back. Reason all that works is that's ordinary arithmetic right here on the real number system, and that's commutative. So we're inheriting a bunch of algebraic properties for the ordinary real number line. And these are just really properties that you would take for granted, not necessarily things you're going to try to memorize verbatim necessarily on an exam. If you look at these again really closely, those are the same kind of properties you're going to see in section 4.1, axioms of a vector space. Every vector space has to follow those kinds of rules. Let me leave that up actually. There we go. So here's our example 2. This one is finally kind of a more honest example, like actual homework problem that you'll see in this section 1.3. We have two vectors. These are coming out of R3, given in this way, u and v. We're going to calculate a linear combination. Now, this is an honest definition. I put it in bold, and we'll show the full definition in the next coming sections. But this would be a linear combination. It means you're taking a scalar multiple of u, a scalar multiple of v, and then performing the vector addition in the middle. So let's write that out. We're going to take 2u, let me try again, I already messed up, 3u minus 2v. It's always good to copy the problem exactly. First thing I would do with this is just do a substitution. Let's write this out as 3 times the vector u, 0, negative 1, 5. And then this one's going to look, I'm just going to put in negative 2 times the vector v, negative 3, 2, and 7. So I didn't really achieve much. I just substituted in the vectors. The next thing we'll do is this right here, the scalar multiplication on both of the vectors. I'm breaking this up into multiple steps because, well, just highlighting each one of these rules. So let's do the scalar multiplication here. We're rescaling 0, negative 1, 5 by 3. That just means multiply all entries by 3. So 0, negative 3, 15. Kind of relaxing math after all those crazy row reduction operations we've been doing in the prior sections. On this one, we're scaling by negative 2, but you do have options. Usually what I do personally, just so I don't get mixed up with sign changes, is instead of multiplying by a positive 2 and leaving a negative in the middle, I'm going to rescale that whole vector by negative 2 and leave a plus in the middle. To me, that's just less signs to take account for when we're running through all these arithmetic operations. So rescale all those by negative 2, and that's going to give us a positive 6, a negative 4, and a negative 14. So that's the scalar multiplication step. What we're left is, well, they're still two vectors. They're different. They've been rescaled. But now we can do the vector addition portion. Vector addition just means add across the rows. In other words, we're adding up all of the corresponding entries together. So in row 1, we'll get a 6. For row 2, we'll get a negative 7. And in row 3, 15 minus 14, we'll get a positive 1. So the linear combination 3u minus 2v results in 6, -7, and 1. And anything like this is what we mean by linear combinations. Scale your vectors, add them up, and that's what we got here. Any questions, folks, on this quick example below? Okay, how do folks feel about these so far? Does it make sense? Awesome, I'm glad to hear that. If you've done work before with vectors, I should mention that our vectors are not the typical kind of vectors. For example, let's scroll up just for a moment. This vector here in R2, 3, -1, if we were to plot that vector, the way we would plot it in this course is we would go x1 entry, x2 entry. So 3, -1 would be 1, 2, 3, -1. And that's how we consider our vector, just a point in R2, that vector space. Some people might write that vector as 3, -1 in a different course. Oh, geez, that Control-Z didn't work out there. And oftentimes when you're writing your vector in this way, you're thinking of a position vector that has an initial position right at the origin and a terminal position right at the point 3, 1. So things look a little bit different, but we're really doing the same kind of algebra here, either way we look at it. Any questions, folks, with that short discussion there? Okay, well, let's go down to, this is a lot of stuff, but you can pretty much take all of this and here's the punchline. Algebra works the way you would probably expect when we put these things together, is the punchline to all of this. Coming down below, now we're going to start doing some conversions. If we're dealing with vector equations, we need to find a way to take a vector equation like this one and get the original system of equations that underlines it. So any system of equations like we've seen in section 1.1 and 1.2, if you wanted, you could write into a vector equation. And if it's already a vector equation, it's good to know how to get that original system out. If this was an exam problem, and sometimes these do come in as exam problems, I usually put in this instruction here just as a warning. This question is just meant to be a really fast concept question, not one where you take a lot of time on it. So I'm going to do 4 using a shortcut that you are welcome to use in the homework. For 3, we're going to do it in a long form way, just to kind of explain what the shortcut would do. And they really go backwards as well. Example 3 says, write a system of equations equivalent to that vector equation. And if we're not sure exactly what that system will look like, some folks might already know, but you could just rescale everything. Here, this is a scalar multiplication, x1 times that vector. Rescale it, and it's 3x1 minus 2x1. And keep on going down the line, rescale 7, 3 as a vector by the scalar x2. I'll get plus 7x2, 3x2. Down the line on the next one, we're going to get -2x3, 1 times x3, so just x3. And it's set equal to 0, 0. So that was our scalar multiplication step. Now we're left with just 3 totally or fine vectors. They're not being rescaled or anything. And we could do the vector addition on all 3 at once. We're just going to now add across the rows on the left-hand side. So it's 3x1 plus 7x2 minus 2x3 equals 0 on row 1. Well, it's going to be 0, 0 coming from over here. Oh, that's way too many rows. Hang on. For some reason, I thought we were in R3 in the middle of the problem. There we go. 0, 0 format there works a little bit better. Same thing on row 2 here. We can add together all these entries to get -2x1 plus 3x2 plus x3. So if we get to this system here, when we've used up all the operations on the vector addition, scalar multiplication, but we still don't have a system of equations just yet, there's one last thing to do. Well, here's the major idea. It seems kind of small, but it's definitely a good point of view to take. We put down vector equality right here. Vector equality is maintained all the way to the last step. If we go up for just a moment, vector equality says this. Your vectors are equal if and only if their corresponding entries are equal. Hold that thought. Let's go down below. These vectors are equal, therefore we must conclude the entries are equal. So this entry is equal to 0. 3x1 plus 7x2 minus 2x3 is 0. Then same thing, corresponding entries are equal means this whole row is equal to 0 as well. So negative 2x1 plus 3x2 plus x3 equals 0. And this is the system of equations. So that's our operations to get to that step. And it's not a bad idea to practice this when you're doing the homework. But if you wanted to, particularly even on exams, notice what we really did. Looking at this original system here, imagine, well, x1 multiplies into all of these first entries. You get 3x1, 7x2, minus 2x3. So all these coefficients are really there for the very first equation. Go to the second equation, coefficients are negative 2, positive 3, and 1. And there they are, negative 2, positive 3, 1. We just attach the x1, x2, x3 to them. And so that's our shortcut. You can really go from here directly down to there in one step. Well, any questions at all, folks, on getting down to that system of equations again?
What would change if the 0, 0 at the end would change to 0, 1?
Oh, gotcha. So if we have a 0, 1 right here, let me put it in. And you know what? This one would be a completely fine problem. We could just leave it like that. All we would change is down here. Exactly. Other questions so far? Okay. Well, now that we're looking at that right-hand side is actually pretty special in a certain sense. We mentioned before, the zero vector plays a particularly interesting role in linear algebra. And there it is as a zero vector. So that means this system of equations and the vector equation, it actually has a name because of that zero. This is called a homogeneous system of equations. Only due to the zero vector there. Here, the right-hand side goes 3, 1, 2. There's no 0, 0 like on the last equation. So this one is not homogeneous. Here we have the right-hand sides other than 0. The reason homogeneity, homogeneous system of equations suddenly becomes really special on the zero vector is, we take just a quick pause. Here's the major things we're going for in linear algebra, and homogeneous system of equations deals with linear independence. So we'll be solving lots of systems with 0 on all the right-hand sides to decide if our vectors are linearly independent or not. We just saw linear combination, we'll define it formally. And in these notes, this is the big one we're hitting, spanning. Spanning is going to be everywhere in this text, particularly, well, chapter 1, let me see here. Chapter 2, it comes into play. Not so much chapter 3, but chapter 4, it's tremendous. And clearly, it's just one of those big things that we have to get used to. Let's go back up to the top here. So we have a homogeneous system. And if this thing has a non-trivial solution, we'll say the vectors here, here, and here are linearly dependent. But for the moment, we're just getting used to writing out the system of equations. And here, we'll reverse the whole thing. Go from the system of equations here to a vector equation, like up at the top. First, any questions or comments at the moment? Okay, well, let's take the shortcut that we mentioned. If you see a system of equations like these, and they tell you write a vector equation, first thing you want to do is extract that scalar x1. It's going to multiply a vector. And any volunteers on what that vector should be? Has anyone spotted it? Exactly. It's revealing exactly what the vector should be just by pulling coefficients. So we're really back to that same theme of what we've done in section 1.1, 1.2, but we're putting it as a vector equation, just a slight format change. So 3, negative 2, 5, and now it's pretty much rinse and repeat. There has to be a plus right here. But after that, go x3. x3 multiplies, so nothing in the middle. We use juxtaposition to indicate the scalar multiplication right there. Now pull coefficients, -2, -7.4, and I did make a mistake there. I'm looking at x2, I should say x2, not x3. That is very, very important for these kinds of systems, so let me fix that. If this was a real homework problem, I probably would go like this and just make a quick correction over there. It would be pretty minor, but it is important, so let's get it in right. That should be x2. Then finally go over to x3, plus x3, multiply by coefficients, 4, 5, -3. For it to be a vector equation, you don't want to celebrate early. There has to be equality for an equation. And now we pull in the right-hand side, 3, 1, 2. So that's an interesting system as well. This one plays a more interesting role in linear algebra because it's tied together with linear independence. But it's important to know how to do it even if it's not a homogeneous system where you don't have zeros on the right-hand side. We did it, folks. That's converting between different systems of equations. The important thing to note, though, is no matter what you're doing here, if your goal is just to solve the system, pretty much what you would do is go to an augmented matrix. No matter if it's the vector equation, a system of equations, we would just take everything, go to an augmented matrix to actually solve it if we needed to. Well, we did it, folks. That's our quick examples of the namesake of this section, vector equations. What we're going to get into next is just more practice with the core terminology. We're going to go for linear combination. We kind of had a preview for it already. And spanning is going to be the most important part of this section, I'd say. So let's keep on going, heading towards spanning as our ultimate goal. We have our definition for linear combination given right here finally. It says, given a set of vectors, here it's listing out n different many vectors, v1, v2, vn. In Rn, we have, hang on, let me look at this really carefully. I think we have a subscript issue. That should have been the P of them. Oh dear, let me put this in red. Sorry for this sudden subscript issue. These things can sometimes be the bane of our existence. That one's correct, but let me highlight it. We have P different vectors coming from Rn, P different scalars coming from the real number line R. The vector Y is going to be defined as this linear combination, C1v1, C2v2, up to the last CP, VP. That seems small, but if you say Cn, Vn there, that's a weird equation saying it'd have to have n terms because that's tied with n. Putting P here says as many terms as you want coming from Rn, so n different components in those vectors. So it seems small, but it's really actually important to put that in there. Let me put that in red. Red here, and I think I fixed some of them. That one was correct. Let me put that in red as well. This one should be CP. One trouble with linear algebra is there are a lot of subscripts. We'll get a little bit more used to them as we practice them more and more. All right, let's try this again with the corrected subscripting. If you have P different vectors coming from Rn, so your vectors have n different components, you'll require P different scalars. This right here is the linear combination. It's set equal to Y, involving those vectors and those scalars. So in other words, if we look at just the last example, we would say that this is a linear combination of, let's say that's v1, v2, v3. So those are three different vectors of v1, v2, v3. But it might be a lie. It says there has to be scalars. That makes this true right here, given those scalars really exist. But here we have a variable. x1, x2, x3 can vary. There might not actually be scalars that makes this true. we would have to find that using row reduction in an augmented system. So we'll say 3, 1, 2 is a linear combination of V1, V2, V3 if and only if this system, V1. So where I wrote V1, imagine we're just putting 3, negative 2, 5. V2, V3, augmented with the right-hand side, 3, 1, 2, is consistent. So in other words, this original system must be consistent, and we're focusing on doing it in the augmented matrix right here. If it is consistent, you can find those scalars, x1, x2, x3, plug them in, and the linear combination would truly exist. There's a way to recombine v1, v2, v3 to get that particular vector right here, is what it would all say. Whew, that's a lot of work. Let's put it in action with our next example down below, example 5. First, any questions at the moment, folks? Okay, so down below here, I included the assignment 3 instructions because I want to focus on this right here. Sometimes the actual results that we have to give in linear algebra, they just feel different from a different math class. Say in a calculus class, you're just giving an answer and then you move on to the next derivative or the next integral and life just goes on. But sometimes in linear algebra, we have to write out a few words to finish off the problem. It'll be something that becomes more and more common, and I'll try to put this here just to indicate there might be a little bit more of a conclusion that's expected to fully finish the problem. Okay, so with that in mind, let's give this a try. It's asking, is B, that vector there, B is playing the same role as the vector Y above in the linear combination. We want to know if it's a linear combination of A1, A2, A3, and that's playing the role of V1 through VP up here in the linear combination. Let's write out the logic for this. We already kind of said what you should do, that's the hint, but let's explain it a little bit better down below. We can say B is a linear combination of A1, A2, A3, if and only if this equation, let's write it down as a vector equation, is consistent. The vector equation would go a scalar x1 times the vector a1, then x2, a2, plus x3, a3 equals b. Let's color code that one temporarily just to show where it's going to be involved. So we have a linear combination if and only if saying this is consistent, forgot to put that in, is consistent, now means we can find x1, x2, x3 that would give us the linear combination. But now notice what they didn't actually ask us in this problem. All they asked is B a linear combination? They didn't ask what are the values of x1, x2, x3 that would result in a linear combination. In other words, we're not trying to solve the system. We just need an echelon form. So let's put that here. This requires only echelon form. We won't use reduced row echelon form for these kinds of questions, unless I told you, find the values of x1, x2, x3 for the linear combination. But that would be a pretty rare question. So let's make this happen. If we're going to solve this system, determine if it's consistent or inconsistent, pretty much all we're going to do is, well, throw all of this into an augmented matrix. It would go like this. Take A1, just throw it in as your first column. So 1, negative 2, 2. And this is going to be relative to the variable x1, since it came from this location. Next, throw in A2, 0, 5, 5. I'll put x2 here. The variables x1, x2 are optional, but sometimes it helps to determine where things are going in the end. So next for A3, it's 208. We'll go right here. Next, augment this whole thing. We're augmenting with the vector B coming from this right-hand side. The equality here, I put it with the dash line. So vector B goes -5, 11, -7. A little bit more color coding couldn't hurt, I think. So that's how we recompile everything all together if you're in a vector equation. And really the way it works is when you see this vector equation, much like say this one, it's really a system of equations like this. You can pretty much read it off. And we just took all of those values here and threw them right into the augmented matrix. Okay, so now that we're here, we're going for echelon form. First thing, we'll take a look at our pivot positions. In the upper left topmost position, we have a pivot. So we'll eliminate entries down below. We'll go row equivalent next. 1, 0, 2, -5 for row 1, won't change. And since we're still getting used to row order reduction, I'll put the descriptions down below here. Let's take and replace row 2. It gets replaced with itself plus 2 times row 1. So back over here, double this, add it to the entry below. We'll get the 0 by design. So now we've got a 0 here and keep on running through this. It'll be 0 plus 5. Multiplied by 2, add it below, we'll have a 4. This will be -10 plus 11 for a +1. Now let's do row 3. Row 3 is just about the same thing, but we'll multiply by a -2 right here. So the description is for the accounting on this, R3 gets replaced with row 3 minus 2 times row 1. So up above, multiply by row 2, add to the bottom row. This one will be -2 plus 2 for 0. No change here due to that 0, so just a 5. -4 plus 8 for a 4. +10 minus 7 for a 3. So we get to this new matrix, and the pivots on this one go position here. We have another position here. All we need to wipe out is that one and see where that work falls at that stage. Well, how's that look to us so far, folks? Any questions at the moment? Okay, let's do our next row reduction then. Now, this one's not too bad. If we were going for reduced row echelon form, this 5 should be changed into a 1. But if you're just going for echelon form, that is not a requirement. And we wouldn't want to divide by 5. We're in the land of fractions. We can just leave it just the way it is. Here's where our operation is going to be to eliminate that 5. Row 3. Let me try again with the right color. Okay, let's try this. So we'll take row 3, replace it with row 3 minus row 2. So just multiply by -1, add to the entries below after the multiplication. So here it's where we'll get 1, 0, 2, -5. I suspect this is our last step, so I'll put in the dash line here. Row 2 will stay the same, 0, 5, 4, and 1. Now here's our operation. That'll be a -5. Let me first put in that 0 there. -5 add to the 5 below gives us another 0. This will be -4 plus 4, so 0. And -1 plus 3, so a +2. So that's our system in its echelon form. Now we have to decide, is this consistent or inconsistent? How do folks feel about it? Does it look good or bad? Some folks are saying not so good. I agree, there's a problem right, oh, didn't mean to scribble on it. Let's pull up the chat first. I agree with Quentin, this is not good at all. Here's a theorem that we should think about when we look at this. We need to know where the pivots are. A remarkable amount of this course is organized by pivots. That's why we focus on the by hand row reduction. We have a pivot here, here, and here. That's the bad one. We have a pivot in the rightmost column, and I mean, there's a couple ways to see why this is bad. If you read out that row, it says 0 equals 2, or you could be thinking of this theorem. This one's a powerhouse. Even though the statement it makes is not large, Always a good one to be aware of. It says the system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. Coming back here, that is a pivot column, so the system is inconsistent. So when you're doing this kind of problem, sure, you'd have to show the row reduction. You don't have to do this work right here. This was more us just getting started, getting used to the problem. But when it comes to this portion, state your conclusion clearly, this is about what you would be writing down for this problem. I'll try to write it down minimally, so this is what I would consider very, very brief. You're not writing down a whole lot. I would write to this stage, inconsistent, so B is not a linear. You can abbreviate this. You might write comb for combination of, you could say A1, A2, A3, or you could keep it in context and just say of these vectors. So that's what I'm meaning by be sure to state your conclusion. So if you say something like this, you've answered the question. It said determine if it's a linear combination. That's the explanation. This is the nitty gritty work, and this is the conclusion right here. Let's just say this whole thing, be sure to state conclusions clearly. Well, we've got it, folks. This vector B is not a linear combination of these three vectors in R3. And you know what? That says something about these vectors. That's three vectors coming from what we consider a three-dimensional space, and we couldn't find a way to algebraically combine them to get that vector. That one is missing. So there's something very, very special about these vectors that we'll discover. We'll later call them linearly dependent. If they were linearly independent, B would have been a linear combination, and there would never have been a pivot right here. We would have been able to make this all work out. So these are a strange set of vectors altogether, for sure. But let's go now to our next example. Oh, and I did have a remark that I want to put here. This is helpful for the homework problem because the question that we just did could be asked in a couple ways. The way we did it is, you'll see this as one problem in the homework, determine if the vector B is a linear combination of these three, or the whole thing could be restated this way. Determine if the vector B is a linear combination of the columns of that matrix A. You're really doing the same thing. They just took these column vectors, placed them in a matrix. You'd still take that matrix, throw it in right there, augment with the vector B, and you're well on your way. Let's tie that together just for emphasis. So that was that short remark there. And the reason I say that here, and I've warned us a little bit about it as a heads up in the homework, our author, when he writes these problems, he is a great wordsmith, and what he's trying to do is expose us to a lot of the terminologies that are common. Sometimes the same problem is written this way, other times it's written this way, and it's the same exact problem. And he makes us see that by asking the same question in a lot of different kinds of ways. So it can be a little bit irritating, but there is a lot of value in the way his questions are written in our text. But here's where we want to go. Here's our next concepts. I restated the definition of linear combination because it's absolutely relevant. What we are very interested about in linear algebra is not a single linear combination of the vectors v1 through vn. We are interested in all of them. We want to know what are the possibilities of every single linear combination that could ever emerge from your set of vectors. When you collect all the possible linear combinations, you're talking about the span of a set of vectors. Now, word of warning, this is our first pretty abstract definition, and it gets worse than that. This is an extremely important definition, like we mentioned earlier, and so we should just make a note. I would consider this a core definition. What I mean by that, it's not as if you'll fail this class if you don't have very good working knowledge of this, but without good working knowledge of this, even passing the class, linear algebra will always feel very foggy unless we nail what we mean by span very, very carefully. So let's see it in three different ways. First, this is in words. V1 through Vp are in Rn, so we have P vectors in Rn. The set of all linear combinations of those vectors is denoted in this way. We say the span of them. It's a subset of Rn spanned by V1, V2, Vp. So we just collect all linear combinations into that object there. Another way to say it is the span of V1 through Vp is a set, and the elements of that set look like this altogether, just generic linear combinations. And set theory is probably a better way to think of it. Sets are something that is very pervasive in mathematics. Linear algebra is no exception. A vector space is a set with extra operations, for example. We'll look at subspaces, which will be subsets of those vector spaces. And so getting used to set notation is a really good idea, not just for this class, but really any work in mathematics. So in set notation, the span of a set of vectors, let's highlight it just to illustrate its importance once more, is written this way. The curly braces are just saying is equal to the set of, or the collection of, these things. These are the linear combinations, so we'll say the set of all linear combinations here we're saying such that. Some books use just a straight line for their such that and set notation. Other books use a colon, but it's always just a stylistic choice. It's always read out as such that. When we form our linear combinations, this is our only stipulation. We're using real number scalars. So C1 through Cp are arbitrary real numbers. Let's just say here, any real number. So that's what the span looks like. In words, it's a set of all linear combinations. As a set, it looks like this altogether. But we want to do even more than that. We want to work with this set, see how to extract objects out of it, maybe graph a span, and just to get a little bit more intuition behind this set right here. Any questions or comments at all so far? Okay, well, there it is, folks. That's the span. And again, this is important to see. We are right here through the progression of linear algebra, some of the major definitions of concepts. Linear combination, defined spanning, and we're going to very soon look at how to define linear independence. And that takes us to chapter 4 type work, where we'll get a basis for a vector space. And finally, we'll give a real definition for what we say dimension of a vector space. We have a feeling when we say R2, it should be dimension 2, that's the plane. If we say R3, that's 3 components. It feels like 3-dimensional space. That should be 3-dimensional. But we need a real definition that tells us why is it 3-dimensional and so on. Especially since vector spaces can be absolutely abstract things, we need a good working definition. So span is our big step forward in that direction, defining the dimension of a vector space. And to really work with this set, that's the purpose of example 6. I want to put here HW to say this is a very similar problem that you'll see in your actual homework. And I think it's tricky, so that's why I'm giving this hint here. The instructions look a little bit vague. I copied them verbatim, so they're a little bit vague here to help out with the homework. We have 2 vectors, they're in R3. We want to list 5 vectors in the span of V1 and V2. For each vector, we'll show the weights on V1 and V2 used to generate the vector and list the entries of the vector. So that's the whole statement of the problem, the way it was written in your book as well. If we want another page, let's just move it over here real quick. And to get started with this problem, we might write out this. We're dealing with the span of V1, V2, so we should just write it out. That's just the symbol for what it is. So span V1, V2 turns into this. It's going to be C1, V1 plus C2, V2. Then we can go such that, either a vertical bar or a colon, completely up to you. I'll go with a colon just to match up the notes. C1 C2 are in the set of all real number line. So set of all real numbers, or the real number line. So that's what we're working with. When it says for each vector, show the weights, this is one of the words our author uses that's synonymous with another word, but he's referring to C1, C2. So in other words, in this course, weights is synonymous with scalars. It's not a bad choice for a word because it's a weight you're putting on a vector v1, so it's kind of visual by using that, but it becomes a distraction since we typically say scalars. So the weights on vectors v1, v2 used to generate the vectors and list the entries of the vector. Well, let's get started. I'm going to write out, when it says 5 vectors, I'll write them out as u1, u2, and so on. So here's our first vector, u1. We were writing u1 as a vector that came from the span. So since u1 is in the span, we have to pick a value for c1. This can be any number you like because the only stipulation is it's a real number. That's it. So one thought is you might decide to work not so hard at first, right? What would you say is the easiest choice for C1, for example? 1 or 0? I think those would both be great choices. Let's use both of them. Well, let's say use 1 here, 0 for there. How's that sound? So if you put in a 1, v1 plus 0, v2, well, we've wiped out v2. Even though this is a scalar, it's going to take every single entry in v2, multiply all of those by 0. This is now the 0 vector. And the 0 vector, because of the addition, well, it's not going to do anything here. It's effectively just gone, like you would have done in ordinary algebra. So we get altogether 1 times v1, that's multiplying 1 throughout here. We have a 1, 0, negative 5. And that's 1 down. The important takeaway about this is this vector v1 is in the span. So when you span v1, v2, you're also containing the original vectors that are generating the set. Likewise, v2 should also be there. Let's do the same thing, put a 0 and then a 1. So I'll call it u2 for the moment, but then let's put in a scalar of 0, multiply it by v1, plus a scalar of 1 this time, multiplying by v2. v1 is now eliminated. v2 is not changed, scaling it by 1. We just get a negative 2, 5, and 0. I don't want to highlight all of these, but here's the next interesting thought. v2 is also in the span of that set. So that's kind of like a set of freebies on this problem. You already have 2 down immediately. And looking at the instructions, when it says for each vector, show the weights, that's what we did here and here. Used to generate the vector, list the entries of the vector. That's what we did here and here. So we're just saying what the outputs are. Well, 0s and 1s are good choices. Let's use all zeros because why not? You could say your next vector, u3, is 0v1 plus 0v2. And notice the way I wrote those zeros. That's a scalar because I didn't put any vector symbol above them. But this now turns into the 0 vector. That turns into the 0 vector. And so I will write them this way to emphasize those are not scalars any longer. That's an entire vector of zeros. We have to list the entries of that vector. Well, because it's a 0 vector, coming from R3, 3 components, we would just go 0, 0, 0. I know I take it back on the highlighting. I feel like the instructions of this problem are so confusing on what they wanted that let's highlight this as part of the response as well. The author wanted the entries listed once we did the combination. Well, does that make sense, folks, on these several vectors we've listed out? Okay, to me, those are the freebies. If I'm going to list vectors in the span of a set, I'm probably going to list v1. I'm going to list v2. I'm going to give it the 0 vector because those vectors are in the side of a span each and every time. But now we need some unique ones or different ones. Here's u4. And I'm completely open to suggestions. We need a scalar times v1 plus another scalar times v2. So we need a value for here and here. How about for folks over in the land of Zoom? Any volunteers for a good choice of a scalar? I know we've got to have someone with a favorite vector choice. Saul says 2, good choice. And how about for one more choice, folks? We've got 2 in here from Saul's suggestion. I like that. Let's put in a 5. And it could be just like that. Pick any choices. Just make sure you're getting a different output. So we're really coming up with 5 different vectors, and you're well on your way. So let's work out this one. 2v1. First, we're taking v1 up here, multiplying it by 2. So it becomes 2, 0, negative 10. By v2, we scale that whole vector by 5, and we'll get negative 10, 25, 0. Even though the numbers are getting big, it's still not too much of a bother just to write it all out. This turns into negative 8, 25, negative 10. So that's our 4th vector inside the span. And, well, we need 5 of them. But you know what a good strategy would be is, if you just want to list 5 vectors as fast as possible, you could use this idea. U1 could be 1 times V1, and always keep a 0 there. I mean, that's allowed. C1, C2 can be any real number. Your next vector could be twice V1, 3 times V1, 4 times V1, 5 times V1, and you're done. You would really be following the instructions to the letter. Those are all vectors inside the span. So let's make our U5 be equal to 2 V1 plus 0 V2. So we're multiplying V1 by 2. This is going to turn into 2, 0, negative 10.
So, quick question.
Yeah.
Who are scalars which represent between 5, do those always have to be different? So V1 and V2, could you, or like U5, could you go 1 V1, 1 V2?
Oh, I gotcha. Yeah, you absolutely could. So you don't have to sit, for example, if you used a 1 here, you could reuse it here and put a 1 there. So as long as you have a unique combination for the scalars, you have a unique answer. It is possible that a different combination of the scalars gives the same vector, but that would be okay for this kind of problem.
Just 1, 0, 0, 0, 0.
Yeah, I agree with that. Absolutely. And that would be allowed. And that's kind of the magic of the set theory here. It doesn't say much, but it really gives you total freedom. Choose any scalars, just make them different combinations of them, and you're all set. And like I mentioned earlier, it is possible with this that you pick different scalars, but you got the same vector. I'm not worried about that if that happened to you. Just stick with what you got, and I think that'd be a fine way to still answer the question. Other questions or comments so far, folks, with working with the span at the moment? Okay, so my emphasis with example 6, the same with the problem that was assigned, is we're just trying to get used to the set, what it's trying to say, how to pull objects out of the set, so we know what even really belongs to that set. And to go a little bit further along those lines, let's actually sketch a span. Having an actual picture in the back of your mind is very, very helpful as well. We could sketch the span of these two, but I'm just not very fluent on a freehand sketch in R3. That's a little bit challenging for me. R2, not so much. So let's give this one a try. I'll never ask you to sketch something in R3, but a question like example 7 is a possible exam question. So this would be just a really fast concept question if it did come up. Let's do it on the next page here. We have V equals a vector 1, 2. We want to sketch the span of V in R2. So R2 is our vector space. Now we can display it this way. It's just the ordinary plane, and we're thinking of the horizontal axis as corresponding to x1, vertical axis as corresponding to x2, only because vectors in R2, if we wrote that one out as a set, it would look like this. R2 is a set of all vectors with entries x1, x2, such that x1, x2 are in R, the set of real numbers. So that's what R2 would look like as a set. As a geometric object, you might plot it this way. Next thing we can do is, let's plot the vector v. Again, we're not thinking of this as a position vector. We're thinking of this as just a point in the plane as our vector. So 1, 2 would go 1 in the x1 direction, 2 in the x2 direction, and that's where the vector v lives. What we really want, though, is the span of v. We have just one vector. Well, to get the span of v, doesn't hurt to just write it out. I mean, this is good practice. It's seeping into your brain every time you write out span v. Let me try again. But when I say writing out span v, this is not what I mean. That's just the name of the object we're dealing with. Writing it out means write it this way. Span v is c times v, such that c is in R. So if we want to generate span of v, just one vector, all you're doing is picking a scalar. And we can do just like we did before, get 5 different vectors, but a few of them should be enough, maybe even just 2 of them. One choice for c, because c can be any real number, is 0 is a great choice, right? So we can say u1 is 0 times v, which would result in the 0 vector. I'll leave it out like this. 0 vector, you could write it as 0, 0 to column vector. It's good to see it as a symbol as well, just written out this way. So it would go right here. There's our 0 vector, right in the origin. If we want another one, we might go u2 equals 2 times v. If we're doubling v, our result is going to be 2 and 4. So let's plot that next one. 2, 4 is going to be 2, 3, 4, about here. Sorry, I'm miscounting my tick marks. That looked like 4 until I squinted real hard. That was only 3 of them. So there's our next vector, u2. And let's do maybe one last one. Let's say u3 equals negative v. We multiply by a negative scalar now this time. Negative v just because it's easy. You might do negative 3v to the same effect. We'll get a result of negative 1, negative 2. Now if we plot this one, here's negative 1 direction, then down 2. And that vector is going to be u3. So we have a sequence of vectors that we're plotting. They very clearly look like they're just going to end up on a line. And this looks discrete, but it's really a continuous line because C came from a continuous real number line. There's truly no gaps here when we look at the whole span. So the entire span would look like this. This is the span of V. Kind of a weird looking object. In the last problem, we had 2 vectors we were spanning in 3-dimensional space R3. The span of those would look like a plane. So imagine this is a plane. It still goes to the origin, but slightly more challenging to draw than, say, this right here. Other things we could say, just for interesting facts about what we just did, R2 is a 2-dimensional vector space. Then when we considered the span, we're not taking every single vector out of R2. This is a subset, but the subset looks like this, and the fact it goes to the origin tells us the span of V is a 1-dimensional subspace of R2. So when we go to take a look at a span of something, we're looking at vector spaces which we call subspaces of a larger vector space like R2. We'll do quite a lot of work on dealing with subspaces as well, back in chapter 4. But visually, when you're dealing with a span, this is what it looks like. You're generating some kind of geometric object. It might be a line, it might be a plane, something even higher dimensional. No matter what the object is, the span of it will always contain a zero vector, the vectors or vector that it generated, and it will be a vector space in its own right. It'll just have a slightly smaller dimension, potentially, than the target vector space it came from. Well, that's our work on span. Any last questions or comments on this example or the prior examples? Okay, well, let's take a look at where we're at so far. I have our example 8. This one looks like it's the last one from the notes. I think we're well positioned to take our time with this one and get through it. So we have two vectors, a1, a2, and a third vector b, 3, -5h. The question they're asking us on this set is, for what values of h is b in the plane spanned by a1, a2? That's kind of a tricky question because of the way it's being asked. It's being asked in a very geometric way. It is a plane because we have two vectors being spanned in R3. But to determine if b is even in the plane spanned by a1 and a2, we can start by just rephrasing the question like this. For what h is this vector b in the span of, we're spanning a1, a2, so that's our whole question. But again, now that we've written this, that's just the name of the complicated geometric object we're working on. Not a bad idea to write out this additional step. Span of a1, a2 is going to be equal to x1, a1 plus x2, a2, such that x1, x2 are in R, the real number line. So this is what we're dealing with. We're wondering, is b inside here? If it is inside there, the only way that could potentially happen is if we take this and equate it to b. So that's going to be our next step. So right now, grab all this, x1, a1, plus x2, a2, if b is in the span, then b must be equal to that equation right here. So now we're back to an ordinary vector equation. The good news is, earlier in the notes, we saw how to take a vector equation, go to a system of equations, or just an augmented matrix. And so now b is in the span. Let's add just one additional notes. B is in span v1, v2, if and only if this is consistent. Consistent now as a vector equation would be the same thing as a system of equations or a matrix equation. So we're just going to take this, no matter how you format it, we're going down to the augmented matrix where all the algebra gets resolved very, very quickly. So here's our next step. We wrote this out just to organize our thoughts. You don't have to do that on a homework problem, but it couldn't hurt just to give you extra practice on this problem. It'll help you out when you see this question again on, say, an exam setting or so on. But from here, go directly to the augmented matrix, pull the coefficients for x1. Where do we find them? We go to a1. Here are all the coefficients, 1, 3, 1. Next, coefficients for x2. x2 is relative to a2, so pull the a2 coefficients, -5, -8, +2. For the equality right here, we'll augment. So here's our dashed line. Next, throw in the vector b, 3, -5h. So all of our work is going to boil down to where are the pivots on this matrix? If the pivots are in column 1, column 2, we'll say that's consistent and therefore B is in the span. But if our pivot is in the rightmost column, then we'll say the system is inconsistent. B is not in the span. So let's give this a try. In row reduction, we already know we have a good looking pivot right here. So we'll just eliminate these two entries right down below. So for the first one, row 2 is swapped with row 2 minus 3 times row 1. So let's write in our row 1, -5, 3 to start. Multiply by -3, add below, will give us a 0. This will be positive 15 minus 8. That sounds like a, oh geez, why am I struggling with that one? Oh, it's because it's late. Arithmetic is the first thing to go when you're tired. That sounds like a 7. Next one is a -9 minus 5, so -14. Let me know if the numbers go sideways. That's remarkably easy to do when you're doing so many arithmetic operations. Now to eliminate that one, this is a faster procedure. We'll say that row 3 is swapped with row 3 minus row 1. So multiplied by -1 and add below will give us 0. Positive 5 plus 2, so a 7. -3, so this will be at h minus 3. So that's where the operation settles down on our first stage. Our pivots now are here in column 1, here in column 2, and all we need to eliminate is this 7 right here. I forgot to add one extra piece of information that I usually would add. Let's put it here. We only need echelon form. So we're using lots of echelon form, but don't worry, reduced row echelon form is going to come back with a vengeance whenever we're dealing with linear independence. It does come back. Well, let's take a look at this. To get this into echelon form, we need to eliminate that 7 right there. And so the procedure will be to take row 3, swap it with row 3, minus row 2. So just a row subtraction. First, we put in rows 1 and row 2. So 1, -5, 3. 0, 7, -14. There's no way that 0 can change, so I usually just write it in. Start the procedure right where the pivot is. So multiply by -1, add below, and we'll get a 0. This will become positive 14, plus h minus 3 will be h plus 11. We're done at this stage. We have a pivot here and here, but this one is in question, right? This one could be a pivot. It just depends on h. So now we're ready to write down our conclusion for this. The question was, for what h is B actually in the span? Anyone see what the right value must be? Exactly. If you put -11 right there, everything is terrific, right? Your system's consistent. That means you could solve for these scalars x1, x2 if you wanted to. But more importantly, B would be in that plane spanned by A1, A2. Absolutely, Prem, thanks for mentioning that. So we'll just go here, throw it at -11, but we still have to write out our conclusion. Nothing too major, we'll just say, well, let me use something that's not a marker. Let's try again. If h equals -11, then B is in span of A1, A2. So that's our conclusion. Nothing major, just a quick blurb to finish off the problem. So I know that you know we really addressed that major question there. Well, we did, folks. That's the last question of the notes. Any questions or comments on these problems at the moment? Okay, well, we introduced a lot of concepts and thoughts on this one. Bigger things are just getting fluent with doing ordinary arithmetic with vectors, scalar multiplication, vector additions, and then the span we'll see over and over again. So learning to deal with the span will be another big takeaway from these notes. Well, that's all I have for folks. Have a great weekend, folks. And if you have any questions that come up while you're working those problems, don't hesitate to email me. Even over the weekend, I'm not on my email constantly, but I do check it, typically in the mornings. And if you have a question, just send it at any time. I'll get to every single one of them, even on the weekends. Well, have a great night, folks, and I'll see you all on Tuesday's class. We'll be in section 1.4.
Thank you.
Yeah, it'll be due a week away from today on Thursday. So yeah, this due date right here would be considered official now. Yeah.
I'm just gonna double check. You want me to email you my assignment if I do it Julie?
Yeah, that'd be terrific. Absolutely. And usually the way you're handing in your assignment, it's really just based on how you want it back. So if you'd like to get your assignment back kind of marked up like this, if that's okay with you, then turning it in digitally is great as well.
I'll tell you everything else.
Awesome. Yeah, it's kind of nice that paper's slowly going away. It's
I
just
know, I got
convenient.
my iPad, like, hey, turn on the picture, and it's really easy just to do it on the iPad, so I got one.
Awesome. Yeah.
Thank you.
Yep. Have a good one. Hello. Doing pretty well, getting through it. I'm still just getting used to the semester. I don't even know my schedule. I just go and to the next thing on it, but getting through it. How are you doing?
Pretty good, tired.
Yeah. Well, hopefully the trigonometry will be a relaxing part of the day, nothing too major.
But the first assignment didn't seem too bad,
Awesome.
but my false sense of confidence could be that I got it wrong.
I'd say you're probably on the right track with it. I think I did see you send that in. Yeah, I didn't grade it, but I looked over it a little bit.